Hello, my dear audience. Welcome to this second video in the series of physics informed neural networks. So, in the last video, what we have done, we have seen that when you have a data which is not of good quality, then the vanilla neural networks they are giving us bad results. So this is what we have done in the first video. So in this video I'm going to introduce physics informed neural networks. So let us see what are physics informed neural networks. So we have seen that there are two worlds, one is neural networks and one is physics, right? So neural networks is, we know that we have basically a data, right? We have a data set which is giving us the things about our model, right? So we have a data set from the model which we want to study, about which we want to predict, and then also there is a physics of that model. For example, what laws of motion are being satisfied by that model or something like that, right? So there is a physics of the model and there is a data set associated with that model, right? In the neural networks we just focus on the data set associated with the model, and in the traditional physics we used to do the laws, just the laws, and we used to solve those differential equation. But now we want to take both of the worlds together, right? And that gives us physics informed neural networks. So it was first introduced in this paper, Artificial Neural Networks for Solving Ordinary and Partial Differential Equation by Leggeris, right? But recently in 2019, when Ricey introduced it again in the paper Physics Informed Neural Networks, a deep learning framework for solving forward and inverse problems involving nonlinear partial differential equations, then it became quite famous. That is because of the advancement in the computational power we have today, right? That is why we can use both the worlds, right? We can use the model as well as physics of the model as well as the data sets, and we can come up with new methods, right, which will be very efficient in solving the models. So let us see what are physics informed neural network. So I will teach you this with an example. Now suppose we have, let us just consider a very simple classic kinematic equation. So suppose you have a ball and you throw it, right? So it comes back to the ground, right? So it's simple motion, like under gravity. Suppose this is the angle theta, right? We already have studied this projectile motion. Many times you have studied it. Starting from your class 9 we are studying projectile motion everywhere. So we already know, suppose initially you are throwing it with a velocity v, then we know that what is the equation of this path. The equation of the path is, it is a parabola, and the equation is v naught. Suppose your initial velocity is v naught sine theta into t, right? Velocity after equation, like position after time t, and then minus 1 by 2 gt square, where g is the gravitational constant having the value 9.81 meter per second square, right? So this is what we already know, right? This we know from like this thing is known to us, that for this particular model this is the exact equation of the path, right? This is the equation of the path. Because this is a simple model, so we could always solve for this particular equation, right? And here we are assuming that this is the height 0 level, right? Okay. So now what we can do is, suppose this is the kind of model you want to study. So what you can do is, you can just at time t, you throw a ball, you can do some experiment. At time t1 you note the position is, what is this height, right? Or just yes, right? So this is basically your vertical position, right? Okay. And at time t2 you again note the vertical position. At time t3 you again note the vertical position. You keep on throwing balls from here at an angle theta, same angle, and you keep on measuring the height after some time, right? So you will have a data set. You will have a data set, right? So you will say that for this particular model I have my data set. Now you put this, what the traditional neural networks do. So you have this model data set with you. So traditional neural networks, what they will do, they have something like this. There is in this, for this particular problem there is one input which is time, right? So this is one input, and then what will happen, you have Suppose this is our first hidden layer. Okay, first hidden layer, right? So what will happen? So you will this will go here. There will be some weight W1, and because this is just one input, otherwise we will put the weighted sum. W1 into T will go here, and then there is also an activation function. Suppose the activation function here is tan hyperbolic, so the output will be there, and then similarly it will go in this perceptron, the output will be there. The weight is W2, right? And I'm putting 1 on the top also to mark that this is the first layer, right? And so on, right? Suppose this is Wn, and then there is a second hidden layer. There is a second hidden layer, right? So here are perceptrons again. So what will happen now? This whatever was output here will be multiplied with some weight, say W11 second layer. This will be multiplied with some weight W121 second, and then this will be multiplied W31 second layer, and so on, right? So this will go to this neuron. Similarly, this will go to this neuron. So we have all the weights here, right? And what will happen? We will have one output, right? And this output will be your y, your height. Okay. So this is the classical structure of a neural network, right? So what will, how the data will be used? So this particular model here, it will put this input T1, right? And initially it will start with some random weights or some weights, and then when we will put T1, we will get some predicted value. Okay, and then you will put T2 in your network, you will get some predicted value, right? Okay, so and so on, right? So what we can do is, but we already have, for T1 you already had some value that y1 will be the solution, and for T2 you already had the value. So now you know the error is what your model has predicted minus what you already had in your data set. Here also, what your model has predicted minus what you already had in your data set. So you have your errors. So what I'm going to do is I'm going to square these errors. So whatever is the predicted value at Ti minus whatever I had in my data set, square it, add them all, right, and divide by n, 1 by n, right? So this is my error. Okay, so I want this error to be minimized because I want my model to perform on the given data set nicely, right? So I'll minimize this, and in the minimization process I'll find what are my unknowns. I want to optimize my weights. So in the process of minimization I'll get the optimal values of my weights, right? So in the process of minimizing this particular function, because you see this predicted value contains weights, so in the process of minimizing this particular term, we will get optimal weights, right? Once I have my optimal weights, so I will say that my neural network is ready. So what I can do now, for this particular problem, you give me any value of t, I'll give you the value of y. Just put it in the neural network, and there will be a forward pass, and I'll get my value of y. So this is that simple, right? So there is no problem in this particular model, but I told you in the beginning that the problem happens when your data set is not good. For example, suppose when you were collecting this particular data set, right? Suppose in the middle of the, like somewhere you slept, so you wrongly measured the height. Suppose this is a faulty data point, right? So suppose there are faulty data points, and the chances are high that when you have a data set, right, there will be human errors, there will be machine errors, there are so many factors which impact the data sets, right? The quality of the data set. So there are high chances that the data set is faulty. So there is no doubt about it. So now when the data set is faulty, so these results are bad, which we have seen in the first video. So what we will do now to rectify this, so we will say that okay, let us not just uh, focus on or rely on the data set. Let us also look at the physics. Let us also look at the physics of the model. Look at the physics. So, if you go to the physics of the model, then you will come to know that the physics of the model is that the second derivative of y with respect to time plus the gravitational constant equal to 0. So, how we derive this equation, that is not we are going to do here, but this is very simple, that we will apply the Newton's second law of motion and we will get it right. Okay, so this is how we will get it. I will tell you, mass into acceleration has to be equal to the force applied, right. So, in this case, if we talk about the position, right, the vertical position, so the second derivative of the vertical position is going to give us the acceleration. So, we multiply it with the mass of the ball, and then the force acting on the ball is minus g, because there is gravity acting into m, right. So, mn and m cancels, so you get t d2y by dt2 plus g equals to 0. So, this is the equation which is being satisfied this for this particular ball, right. And if you look at the initial condition, now if you look at the initial condition, what is the initial condition? So, you want that the height at 0 is 0, at the beginning you are giving no height, and also the initial velocity you are giving, right, dy by dt at t equal to 0 is v sin theta. Why v sin theta? Because this is how you are, v not sin theta, you are throwing ball like this at an angle of theta. So, this horizontal velocity component is v naught cos theta, and the vertical velocity component is v naught sin theta. And then we also want the final position to be 0. So, we want at the final time the ball should hit the ground again. So, y at t should be 0, right. So, this is the physics of the model. Now, these are the equations which tells you the physics of the model, right. Okay. So, what we are going to do, we will say that we already had this term, right, 1 by n I from 1 to n y predicted at the time ti minus yi square, right. So, this we already had from the neural network. This was the error we were minimizing, right. So, we will call it as error from the data, right. But now we will say that error is also, if this y predictor does not satisfy the model, then also there is an error. So, what we are going to do, we will say that this y predicted, whatever is my y predicted, if I take the second derivative, right, at the position ti minus plus g, this is also error. If this is not 0, because I want it to be 0, if it is not 0, that then also I have a problem, because I want my predicted values to satisfy the physics of the model. So, this also I will include, right. This also I will include I from 1 to n, 1 by n. So, I call it as L physics, right. So, this was my L data and this is L physics. But then also I want to satisfy initial and boundary conditions. So, these are initial conditions and boundary conditions, right. Here these are initial and boundary condition. So, I want my y predicted at 0 should be 0. So, minus 0, okay. And then I want second condition, what I want that y predicted, if I take the derivative with respect to time at 0 should be v naught sin theta. Then also I want that y predicted at the time capital T should be 0. So, all these errors I will add them I from 1 to n, and then I will do this, right. Okay. So, this is my boundary condition and initial condition error. Okay. So, do you understand? So, I will not do this I from 1 to n here, because this is not, there is no I here, right, because I am just looking it at a particular value, for example at 0 or at t, right. So, there is no need of this term here. Okay, let me this one. Okay. So, this is our error from the initial and boundary condition, right. So now you don't just minimize this particular error, you will minimize this error as well as this error as well as this error. So what you are going to do, you are going to construct L total, which will be lambda 1 times L data plus lambda 2 times L physics plus lambda 3 times L boundary conditions and initial conditions, right. So what we are going to do, we are going to do the same thing. We have the data set and we have the physics now also. So we will put it in our neural network, we will get some predicted value, right? So you'll get some predicted value. For that predicted value, you are going to compute your L data, L physics, and L boundary condition, initial condition. Then you will try to get your weights in the process of minimizing this particular term instead of just minimizing this term. You see what you have done here? You have used both the data set as well as the physics of the model. So this is called physics informed neural network. So you get your weights, you get optimal weights by minimizing this particular quantity. Okay, so this is called physics informed neural networks, right? So now what are these lambda 1, lambda 2 and lambda 3? So these are called hyperparameters, right? So these are called hyperparameters. So you already know that what are hyperparameters for neural networks. So this, what, how we are going to choose them? So for example, somebody is very much sure that my data is very good, so he or she would like to have larger value of lambda 1. So we should have lambda 1 plus lambda 2 plus lambda 3 equal to 1, right? So what is a component, right? And somebody who is sure that this data set is, generated by one of my lousy student who is not, serious about his work, so he or she would like to have this lambda 1 very small because they don't want to give importance to the data set, right? So something like that, that is how you are going to decide your lambda 1, lambda 2 and lambda 3. So you see, this is a beautiful thing, that we are going to use the data set as well as the physics of the model to optimize the weights in the neural network, right? So once you get your weights using this particular minimization, it is a physics informed neural network. So it is physics informed neural network. So you see, this is now your physics knowledge as well as your machine learning or artificial intelligence knowledge is going to, come together, and they are going to go together instead of just leaving your physics behind and traveling into another world of data. That is not a good idea, right? It is always said that you should always be connected to your past, right? So we should not forget the physics which we were doing for a long time, right? So that is the idea of physics informed neural network. So I hope you understood it well. If you want to get into details, you can follow these videos, and also this is a good paper, both of them. You can read these research papers and you can find out what they have done earlier, right? We will also do the coding and all those parts for physics informed neural networks. So stay connected. Please share this video with anybody who is, starting to learn physics informed neural network for computational fluid dynamic problems or any problems, right? Thank you for watching this video. Please share this video and subscribe to this channel. Happy learning.